I started here about 3 years ago. And about 3 months into working here as a data scientist, my first data science job that I've ever had, I'm working on a project and I think, wouldn't it be great to get some test data? So I'm thinking, okay, we have this device graph that's supposed to be sort of, the Kool-Aid that I've been sold is that it's a small household within a larger sea of graphs, so these little islands of devices. And I'm like, well, I'm clever enough. I'm going to randomly grab a device. I'll do some depth first search. I'll get all the devices it's connected to, and I'll have a nice sample set of different connected components. So I run my code. Everything's looking great. All my tests are running great. I sit on a device. I get the first cluster. It's small. It's reasonable. It's 10, 15 devices. I think this is working wonderfully. Get the second cluster. All's going well. And I sit on the third cluster, and it just keeps going. And I'm thinking, like, why is my job taking an hour to run? I'm not that bad of an engineer. And then I stop the code, and I look at the output, and I realize that I have something like 10,000 nodes accumulating in this cluster. I'm like, oh no, there's something seriously wrong. And that is when I coined the term Sharknado cluster, because it was 3 years ago, and the world was a little different back then. And so that's when we realized here at Tapad that if we wanted to understand the graph, we were going to have to figure out how to solve the connected component problem at scale. First, I'm going to solve the computer going to sleep problem. And then, okay, that's the end of that. Okay, so I'm a data scientist. I came to Tapad 3 years ago. My background is in chemical physics, so cut me a little slack if I don't know the big O of every algorithm I talk about. I'm not going to talk about classifiers. I'm not going to talk about data science. I'm actually going to talk about engineering. This is the perfect crowd for this talk. So I'm going to tell you a little bit about Tapad, because I don't think anybody knows what we do. So Tapad is a marketing technology tool. This is Adtech. What we're trying to do, essentially, is find a way to probabilistically link people across their devices. So you have a phone, you have a computer. We want to be able to leverage information that we get from our ecosystem about your patterns on your phone. Let's say you are interested in buying the functional programming in Scala book. So you put it into your cart in some web page, but you're still thinking about it. You're like, well, maybe I want to buy it for Haskell. For some ill-advised reason. So then, you don't buy it, and then maybe we think, like, well, maybe on your phone you'll be more susceptible for some reason. So then we'll show you this big, shiny red ad for this amazing book, which you should all buy, actually. So that's what the goal of Tapad is. So the way that we think about our solution is as a graph. We have the device graph. It's trademarked. So we are the one and only the device graph. And we try to connect people's computers to each other through probabilistic linkage. The problem, as I just explained to you, is that modeling identity is really hard. So you have identifier persistence and accuracy issues. We sync with lots of different partners, and sometimes we can trust them, and sometimes they'll send us the same identifier for 1,000 devices. That's not good. So we have conflicting data. Sometimes we sync one of our cookies, and a different partner will say, no, actually, we think that's two different devices. How do we reconcile that? We have issues with grouping keys, which is exactly the problem I'm describing to you. How do we define a connecting component in our graph? We have privacy issues. We definitely do not want to know that this graph represents Daniel, for example. We want to know this graph represents an entity without a name, a social security number, an email address, or any fingerprinting technology. And then we need some use case flexibility, because we're actually sell our data as a licensing tool. And if you would like to license our data, you should talk to Toby. I don't know if he gets commission, but you should. So I'm going to talk about two things, identifier persistence, like persistence in time, and also grouping keys. So that's the connected component part. And I'm going to tell you about two algorithms I really like. And I think that I've found their use cases sort of vast in number. So I'm going to tell you a little bit about identifier persistence. So grouping keys, how can we effectively group keys at the scale that we're talking about? And I'll tell you about that in a second. And then also, how can we make sure that those identifiers for those groupings are consistent in time? Okay, so I don't have any classifiers, I have no recommendation engines, and no community detection. So I think that I have to turn in my data science badge after this stuff. So this is what our graph looks like. Our front-end engineers are very talented, and they built this very lovely visualization. And so what you can see is, since the early days, we have cleaned up our Sharknado issues, and now our device graph really is made up of small, independent subgraphs. But the problem is that there are 1.4 billion of them. There are 6.6 billion connections between them. And so how do we actually determine these little subgraphs? How can I identify that these 7 to 50 devices are actually one single unit? So we'll go through sort of the most vanilla version of a message passing algorithm. I can tell you that it doesn't work. We've tried database technologies which claim to be able to efficiently cluster our graph, and we have just not been able to make it work for us. So we had to roll around. Okay. And the current solution that we do run, it actually runs in logarithmic rounds, which is really fast, which means we can cluster not just our devices, but all of the identifiers for the devices, of which there could be, at 50 identifiers for every device. So 50 times 1.4 billion is a lot of billion. So the most basic thing, a lot of you are engineers, so maybe some of you are familiar, but for those of you who come from maybe less traditional backgrounds or data scientists like myself who are not familiar with label propagation in a graph, I'm going to go through it. So the first thing you do is you have a cluster. I have chosen this very nice cluster, which is just linear, which is actually the worst case scenario for label propagation. You say, I'm node A, I'm very self-centric, and I will assign myself as my label. So in the first round, you get A, B, C, D, and these are temporary labels. And then in each subsequent round, what's going to happen is you are going to ask your neighbor, what's your label? And decide whether or not you prefer your neighbor's label or the current one that we have. And in this one, we choose to use the minimum. So you will always prefer the minimum label. So you had A, B, C, D. So A is going to ask B, but A is still smaller than B, so it's going to retain its label. B, on the other hand, is going to ask A and C. Now B notices, hey, A has a better label than me, so I'm going to steal A's label. C asks B and D. C sees that B has a better label. At that time, that label is B, because this is happening right afterwards. So it doesn't yet know that B is also getting a better label. And then last but not least, D is going to ask C, and it's going to update to C. So in that round, you'll get A, B, and C. And then the subsequent round, the A will propagate over, the B will propagate over until the whole cluster has become A. And then once there are no changes from one iteration to the next, then you know that you have sufficiently labeled all of your clusters, and you just give this cluster label A, which is unique because you only have one node labeled A in your graph. That's pretty basic. Think we're good? Okay. That is very slow. If you have a very long linear chain, which we occasionally do, to sit there and actually do that, in 1,000 rounds, which may occasionally happen, would be very hard to MapReduce because it would be 1,000 MapReduce phases times a few extra here and there. It's not something you want to play with. So we found this really cool paper about finding vector components in MapReduce and logarithmic rounds. One of our engineers, Garrett, he was very kind as to implement it for us. So I'm going to actually tell you about it and steal all of his glory. So if the old algorithm, just to give you a sense, runs in the diameter of your chain, roughly, that's how many rounds it takes, this one's going to run in the log of the diameter. So it's called Heshtamin, and I'll tell you a little bit about it. I like to do it in pictures. I think it's better that way. So when you initialize, essentially, you have the same kind of setup. You have these nodes, and they have their labels. And the first pass, for every node V, you assign the minimum of V and nearest neighbors as its current cluster label, and you also define a cluster C of V, which is at the time just the set of itself and its neighbors. So A initially is going to get label A, B is going to get label A, C is going to get B. It's almost like if I did the first pass of the previous algorithm. And then CV here is going to be just the set of neighbors and myself. So A set is A and B, B is A, B, C. C is all of its neighborhoods, so it's B, C, D, and E, so on and so forth. Okay? Alright, so in the first pass, round 1. So for each CV, you find the minimum value. So for this guy, it's going to be A. I really want to be. Is that better? Is that better or worse? Better?
A little higher.
A little higher. Better, 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 less, okay, good. So you see A is going to get A is going to find the minimum A, B is going to find the minimum A, C's minimum will be B, D will be C, and E will be C. Okay, so we've computed that, that's good. So then what we do is we broadcast CV, so the whole set that's in here, to the one that we just found is the minimum. So C, for example, will broadcast this entire set to B. And then, in place of it, we'll only keep B as a record of where it sent the data. So we'll say, I'm going to give up all of my data to the best candidate for the label, and in its place, I will only retain the information about where I sent the data. So each node V then merges all of the CVs that it gets. So as I just said, C is going to send all of the data to B. So B will now have all this in addition to whatever it has, as well as the minimum it gave itself, which is going to be A. So B in the meantime will have sent all this data to A, retained only A, but in the same breath it's receiving all of the data from C, because C thinks that it's the best candidate. So that's going to look like this. This is the update. So A has now received the data basically just from B, but B has actually received all of the data from C and has retained A as a memory of where it itself sent its data to. It's a little, not the clearest thing maybe. So, and then you keep going with that. So you continuously send all of your data to your current minimum, and until you have, everyone just has basically a pointer to the top, and you export all of your data at the same time backwards to everyone else. So what's also happening, right, is as B is sent, let me go back. So at the same time that C is sending all of its data here to A, it's also going to tell D and E, like a trail of breadcrumbs, by the way, I sent you to A. So it's going to broadcast this value out to the other guy. So it's almost like it's sending the majority to the minimum and then sending the best one to everyone as sort of a trail back to where it came from in both directions at once, which is exactly how you get the logarithmic maps. Because you're going not just in one direction, you're actually propagating the label in two directions at the same time. Okay, so you end up completing a logarithmic round and you end up ending when nothing has changed. The same exact stepping criteria as the standard label round. This is the last round, and you'll see that A has all of the information, and the other nodes now, they themselves know where their data was sent. They know which node they are for. Any questions about that? Yeah?
Is CV a label or is it a pointer?
CV is, it's both simultaneously sort of a pointer and also the set that you belong to. So if you contain more than one thing, then you are probably containing sort of the list of all the devices in that set. If you're containing one thing, it's often representing a pointer. So CV is sort of acting for two reasons. It's in one direction, it's a pointer, and in the other direction, it's actually the set of all devices in the set. So when you finish your algorithm, if you are node C and you see that you have anything other than yourself in here, you know that your entire cluster is, you just point to this to know that that's where you look for the membership of that cluster. So like, if you're not in the cluster, then you point to the cluster. Then you point to the cluster. That's the distinction. So once we have the connected components, we have a second problem. So we work in Adtech, and so we build our graph in batch every week. So every week we build our graph off of 6 days of data. Now the problem is our campaigns, they don't just run in the space of a week or a few days. They run in the space of weeks, months, in some cases. And so we really want to be able to track not just what happened today, but tomorrow and yesterday. And so doing that means we need to find a persistent way to label our clusters before. So the current scheme that I just described to you is you just take the minimum value. Right? So you have this cluster, A, B, C, D, E. You take its minimum, that's A. That's our old way of labeling things. And what we found is that week over week, only 78% of devices have the same label. That's not something you give your salesperson to sell. They don't like numbers like 78%. They think that's not good enough, because if 78% is dropping off every week, after 8 weeks, my cluster is labeling for any given device only has about a 1 in 5 chance of being the same. It's not good for following users advertising. So why did 22% of devices change their label week over week? So there's sort of two classes, and there's sort of this class which I call the acceptable reasons for a cluster change. That's ID expiration and creation. So in the ID space world, you have clusters that are, you have devices that are turning their cookies. You have people buying new devices, and so you have all kinds of reasons why a new node identifier might enter your graph. So you get things like a device expiring. So you see in this case, B, if this is week 1 and that's week 2, B has disappeared. Maybe it's a churning cookie, maybe it's a device that I accidentally spilled tea all over. For those of you familiar with my tea drinking habits, you'll know how likely that is. Or, your new Oculus came out, and suddenly we're going to serve you Tapad advertising while you're playing your very vertigo-inducing virtual reality game, and now a new label has entered our graph, and therefore the cluster has changed its label. So the character of these clusters has not fundamentally changed. Just you got new devices and you lost some devices, and that's totally fine. Okay? And then there is the second case, in which case this is a little bit less palatable, let's say. And that's you have cluster splits. Now, short of occasional very bad breakups, we don't really want to see this kind of behavior very often, because it means that we sort of made a mistake somewhere. And we make mistakes. We just don't like to make too many of them. Or you have the situation where two clusters merge, which is the opposite. And as much as we like to think of us observing the good work of OkCupid, we actually think this is probably more likely another time we made a mistake. So what is the split between them? So it turns out actually more than 75% of the 22% are the sort of acceptable changes. New devices being created, old devices going out of the graph. Only about a quarter of the 22%, so only 3 or 4%, are going out because of what we would call unacceptable reasons. Mistakes that we've made in our algorithm. So the solution to this problem is maybe an algorithm you haven't thought about since your undergrad days, the stable marriage algorithm. I'm very sorry for the heteronormativity of the Wikipedia article, but this is what Wikipedia says now. So given n men and n women, where each person has ranked all members of the opposite sex in order of preference, marry the men and women together such that there are no two people of opposite sex who would prefer each other than the current partner. When there are no such pairs, the set of marriage is stable. It's sort of a confusing thing. So instead of men and women, I'm going to use triangles and circles, because HR says I could not use men and women. It's my own personal beef with this. So it's a proof by negation. So this is an unstable marriage. So this is essentially your circle is your Romeo and your triangle is your Juliet, and they've been married off to someone from their own clan, but they would rather be with each other, right? So they'll leave their partner to be with each other, and that would cause instability in the marriage. and you'll have some lonely people on either side. So in the case where basically this circle could still prefer this triangle, but as long as this triangle prefers this circle over that one, we're good. Because in that case, this triangle is like, I'm not trading up to be with this circle, so I'm good where I am, right? So that's a stable solution. There are actually, stable solutions are not unique. You can actually have multiple stable solutions. So just feel good about that as you go out in the world looking for love. So the algorithm is the Gale-Shapley algorithm. So we have triangles and we have circles, and I'm a physicist, so I gave them reasons. But this is, A, B, C, N, beta, gamma, delta. By the way, this algorithm won the Nobel Prize in Economics in 2012, so it's a good one to know. So the first thing you do is you basically rank all of your partners. You say, I really prefer beta. Beta is great. Beta has the best record collection. So I'm going with beta. Gamma's okay, but spends a little too much time on Pokemon Go. And then delta only knows Haskell. So that's the bottom. And so on and so forth. You see that you rank everyone, whatever your criteria is. And then what you do is you pick a side that proposes to the other. Unfortunately, only one side gets to propose. So in this case, the circles are proposing to the triangles. So in the first round, each of the circles is going to propose to its best. It's going to go for the goals, like I want the best I can get. So I propose to the best one. And then the triangle, if it has anyone proposing to it at the time, it will pick the best of its series. So this triangle here, it only got one proposal. So it's like, okay, well, what I got. So it takes it even though it's its third rank. Whereas this triangle is in for a treat because it cannot pick. So it picks delta because that one is better. So unfortunately, A is still out in the cold, and beta is about to be rejected. Beta will be rejected. Okay, so I got 2 out of 3. Let's keep going. So then beta now gives it another go, and it tries for its second best match. So beta's second best match actually B. And B, now seeing that it has a new suitor, is like, well, I can trade up. I actually prefer beta over gamma. So it says bye-bye gamma. And it's now in the cold again. We keep going until there's a one-to-one mapping of proposals to accepted marriage requests. That is how you run a stable marriage algorithm. Any questions about that? Probably a lot of you know this algorithm from your algorithms course or something. The rest of us who spent too much time in classical mechanics did not get this luxury. So how do we use it at Tapad? So there's a couple of things. In order to run this properly, we had to rank cluster pairing. So we have a clustering at week 1, we have a clustering at week 2. How do we rank the interplay between these clusters and those clusters such that we map one cluster label onto another? That's just part of our sequence. We need to be able to run it at scale for 100 million label points, and that's like 100 million clusters. And we need to run it in MapReduce, which we do. And we need to be able to handle things like ties. And we also have to be able to handle what I call the CNN projected Donald Trump effect in November, where large households all move to Canada, which means clusters wholesale disappearing and clusters wholesale appearing. I assume that there'll be some Trump loving Canadians who will also move here, but we haven't heard much about that. So, great. So it turns out we went from using this algorithm, we went from a 78% consistency in week over week labeling to a 98% consistency. And salespeople love things with a 9 in front of them. They're really excited about it. So now actually we sell this, and just last week, Toby's team launched persistent cluster IDs in our data product, which is huge for us. And it turns out we went from 8 weeks out having 33% consistency to now almost at 90%. So our 8-week consistency, mind you, our graph is built on about 8 weeks of data. So that means almost no data overlap between these used to build the graph is now better than our 1-week consistency before. So the conclusions, these problems are problems for the data science team. and they were not data science problems. They're engineering problems. Unfortunately, data scientists are not always good engineers, which includes me. But it would have been great if I knew these algorithms beforehand. So, and sort of speaking to the choir, I guess, right? Speaking to the choir, data scientists knew more about engineering algorithms. We could be even better data scientists, because sometimes people throw problems at us that are not data science problems. Instead of building some horrible community detection algorithm to do this, I wrote a Yael-shaped algorithm. This is so much simpler and so much more elegant. And once you start seeing this, you start stable matching everything. So anything that you can have like a matching to, you can stable match. Anything you need a one-to-one matching to. Anytime you have anything where you have pairs of things, so for example, you build a correlation matrix, and you want to find clusters of correlated things, you can run a connected component algorithm if you believe your matrix is very sparse. So these algorithms are really not limited to the problems that I developed them for. You can really go out and use them for so many awesome things. And in fact, since we've developed these algorithms here, we actually use both of them for at least 3 or 4 use cases at this point. For persistent, not just persistent cluster IDs, but now we actually use it for persistent device identifiers. Been looking at it for a bunch of other things that we want to keep persistent in time. And for connected components, we don't just run it on our graph, we run it on our device identifiers and also on some correlation matrices that are pretty sparse. Okay, so I really want to thank the data science and engineering team because they really helped everything here, and they've actually done a lot of this work, cleaned up a lot of my work. We have jobs. We have so many jobs. Please come work for Tapad. It's awesome. I've been here for 3 years, which says a lot because, as you know, in startup world, 3 years is like your whole career. And you can follow us on Twitter, or you can follow me on Twitter. You will occasionally see me ranting at different postal services there, so I apologize in advance. Thank you. Any questions? Yes?
What kind of data do you collect on those devices? So
What kind of data do we collect? Yeah. So we collect the standard Adtech bid requests, if you're familiar, data, which is things like user agent, device ID, the URL that you're browsing on, the timestamp, the IP address. That's, basic Adtech data. So. Yeah?
Which libraries did you use to help you solve these problems?
There are no libraries here. Is Scalding a library? I don't. Everything here is actually written in Scalding. Pretty basic Scalding. There's no data library here.
So you mentioned that you have these split issues.
Yeah. I'm sorry?
You mentioned the split merge issues.
Yes.
The number of people mistakes. Can you look at mistakes?
Our algorithm is probabilistic, so we don't actually know for sure that any of our linkages is 100% correct. So if occasionally we accidentally bridge 2 users because our algorithm makes some sort of false positive, that could accidentally merge them, and if it gets corrected because that piece of data goes away and our next source and better data comes along, that will be an issue that get corrected. It's just the nature of probabilistic algorithms. Yes? Yeah. Thank you so much for having me.
Thank you.